So Dstillery, we're an applied data science company. We build predictive audiences for targeted advertising, and we use machine learning to better understand customers so that marketers can craft and deliver advertising more effectively. So the application I'm going to talk about today has to do with customer segmentation. So this is kind of like an age-old staple of market research. The way they usually do it is they recruit a bunch of people, they either put them in a room in a focus group or send them surveys and ask them questions, and then sort of group similar customers for a given brand based on what they answer. I'm going to talk about a way to update that classic view. Oh, cool, clicker works. I'm going to talk about a way to update that using neural networks, in particular semantic embeddings, in order to understand like a really detailed view of web browsing behavior. Thank you. And use that to update that classic view of customer segmentation. So I have a couple slides kind of explaining the business motivation for this particular approach to clustering. So if you're here for the neural networks and embeddings, hang with me, we'll get there. First, talk about marketing. So it all starts here. Who's my customer? Any brand needs to start with this question. Once you understand what your customers' motivations and interests are, then you can start to design the messaging and understand where to find them. So it's, you're doing messaging and targeting based on who your customers are. But obviously, any brand doesn't just have one customer. And so brands know this. They know they have lots of different customers, and there's different people that are drawn to their product for different reasons, right? So they want to understand the different reasons someone might buy their product. If you imagine that all of these people are customers for an indoor fitness bike, you could imagine if you were able to tease apart separate groups of customers based on their reasons for buying it or their interests and their motivations, you might start to identify new groups of customers that you previously as a brand didn't know about. They were in your blind spot. So for instance, in this case, once we can do this, we can identify that there is a small group of people that the reason why they're buying this exercise bike is because they're gamers and they're sort of drawn to the tech in the bike and the sort of level up experience of riding that bike. So this is something that once the brand knows this, then they can start to invest in different messaging. Maybe this is a small growing market that they want to invest in. And in order to do that, they have to know about and they have to strategize for it accordingly, right? So how are we doing this? We're doing this with web browsing behavior. There's a couple advantages to the type of data we're using. I'll show it to you in a second. When I show this to marketers, the reason why they're really excited, the main reason they're usually excited about using web browsing behavior is because it's observed rather than self-reported. So they don't have to rely on people being good at answering questions in like an honest way with good memory and good sort of introspection. But actually, I think that the reason why this data is effective especially for identifying these sort of previously unseen groups of people, has to do with how broad it is and how granular it is. So this is the data we're using. It's web browsing behavior. It's collected at the cookie level, and it's like an event level stream of time-stamped URL events. So we're seeing this across, we have a view of over 400 million browsers. We're seeing this across over 10 million different websites. And the way we get it is from two sources broadly. So one is that we're plugged into the real-time bidding advertising framework. So we're seeing all the ad requests when someone shows up on an ad monetized site. We have the opportunity to show an ad, and we have a view in some cases of where they are, and we can use that. And then the other source is there's companies that produce like web development tools that they provide. Web developers put them on their sites in exchange for this view of which cookies are coming through the site. So it's a really broad view. So stepping back to the segmentation problem, the reason why I think that this type of data is really well suited to that problem is first, if you want to identify a group of people that is small and sort of hard to notice, by definition, it's really hard to do that using survey type data, because if it's a small group of people, you have to sort of look at a lot of people in order to find them. And that's hard to do if you have to recruit people to take your survey, right? So the fact that we're looking at so many hundreds of millions of browsers is really helpful for finding small groups. Also, just the breadth of the type of signal that we're covering. both like the specificity of individual URLs, but like really importantly, the fact that we have this view of ad-supported behavior, non-ad-supported behavior. It's like a very healthy cross-section of kind of all of this stuff that happens on the internet. And so it's a lot of colors in your palette in order when you're trying to paint a picture of a customer. It makes it much more likely that you'll find something that you didn't expect that you might not have known to ask a question about in a survey. Like for instance, are you obsessed with video games? If you're talking about an exercise bike. So why is this hard? So this is my data set, right? The entities look like this. Every entity in my data set is a user, and the feature is all these website visitations. I've explained this clustering to clients, I explain it to them all the time, and I never need to tell them how it works. I just say, okay, so we take your customers, we have their web browsing behavior, we cluster them we cluster similar users based on their web browsing behavior, and there you have it. And no one ever blinks. I think so why is it harder? I think if they're picturing something, they might not be paying attention when I'm telling you this, but if they're picturing something, I think this is what they're picturing. So you have these users, each one has some set of websites that they've been to. So okay, very straightforward. If they have a website in common, then those two users have more in common. So we say that the ones that have more websites in common are going to be closer together. We can define this mathematically. It's probably not what my clients are thinking, but you can define, say, like a cosine distance, like 1 minus the cosine similarity I'm showing here. So this is essentially a measure of the relative overlap of the history between these two users. So how much of their browsing history do they have in common? Once you have this, then you can define pairwise distances between every set of users, and then you can make a nice pretty dendrogram like this, where users that are more similar to each other are linked like lower on this particular plot, and then you can choose to cut it wherever you want for like whatever your purposes are. You want 4 clusters, you cut it right here. If you want more, you cut it lower. So simple, right? We have all the data we need, so no problem. So why is this hard? Is because our data actually looks like this. So I said we have tens of millions of websites. So it's a super large data set, and it's super, super sparse. And any given user is only going to have a tiny fraction of these columns filled in with any number. So then when I go to look at what kind of distances I get between users, so now I'm looking at real data. This is a set of users that are all users for one particular brand. So they actually have a lot in common. And I've calculated their cosine distances, pairwise cosine distances for every user. So I made that distance matrix. I took the upper diagonal, and I threw that all into a histogram. And this is what you get. And so there are a couple problems with it. One, no one seems to really have anything in common, right? So in particular, the way you see that is that most of the distances are kind of like maximally large, and there's a very small set of people that have sort of enough of their content is overlapping that they have sort of an interestingly similar distance, and so there's a very small tail here. And then the other thing that I think really gets to the meat of it a little more is not only are they all the users look different, but they're all sort of equally different. So we have a really narrow distribution of distances, and we don't have any sense of like a gradation of who is more different from who. And so what you end up with, because of that, is this picture where, in the best case, you just have all these tiny, tiny clusters, each as different from the next as the next one. Like there's not anything to bring them together because it relies on having overlapping content to find those similarities. So to be a little more concrete on how you can imagine this end up happening. So here's 5 users, hypothetical users. And let's focus on the top one here that's highlighted in red. So this user has been to CNN.com, weather.com, lovecrochet.com, and justcrochet.com, okay? Now, the distance between this user and the user that's been to only CNN and weather.com is exactly the same in cosine distance as this user who has been to lovecrochet and justcrochet.com. Whereas, all of us as humans looking at this can see that that's clearly a much more interesting similarity that maybe deserves, some special consideration. When you treat every website as tokens, this is all you get, right? So that's really the key of it here, is that we're treating these categorically. We don't have any extra information besides yes or no for each one of these things. There's not enough context. It gets worse even. So if you look at this user that's been to crochetandcreate.com and crochetspot.com, clearly they have a ton in common with this user. They're one of not that many people that is obsessed with crocheting, right? And this same thing with this person who's been to a couple of knitting sites. There's no way to connect them. By this measure, these people are all completely different and they have 0 similarity. And then even worse, if you look at the users that aren't connected here, in this model, they're all equally different. There's no measure of different amounts of someone being more different from someone else. They have nothing in common, so they're different, end of story, yes or no, right? Okay, so clearly we need some kind of dimensionality reduction, right? We need a way to bring more context in for each of these users. One way to do that would be to add categories to the websites. And you see this helps, right? So now we know that those two crochet websites are crochet websites, and we're able to find more similarities. So you get more overlap. With this approach, you actually do get a little bit nicer of a dendrogram. But the problem is you really kind of just pass the buck, right? We're still dealing with categorical variables. You still can't tell that this knitting person has any more in common with the person that loves crocheting than the person that's interested in the news. So really what we need is a representation of a user that contains more context and is sort of less categorical. So what we want is to go from, rather than having this sparse binary representation, so that first view was a sparse binary vector, was a representation for one user, right? What we really want is a continuous distributed vector. So there's information that's spread out along more dimensions, and it's not just yeses or nos. So this is the histogram I showed for that sparse binary vector. If you had a better continuous representation, you might get something that's a little more spread out like this, and then you get a nice dendrogram. And these two pictures on the bottom are actually the real results with real data of the method that I'm going to show right now using website embeddings. So let's start by addressing that representation of my features, right? So my real goal is to get a representation of the user. That's a dense, continuous distributed vector. But I'm going to start by tackling the features and try and get a better representation of just the websites alone. So let's try and see how we can find a distributed representation of websites. So websites actually have a lot in common with words, right? So you can do, in NLP, you can do a lot with words just treating them as tokens. And there's a lot of useful work that's been done that way, but clearly the individual words have more meaning like that, and it's not the case that each word is as different as the next. And so one approach that's been used to really effectively bring more context into words is Word2Vec. So this I just pulled from the TensorFlow webpage, Word2Vec on a set of words that were related to literature. So Word2Vec is an approach for finding distributed vector representations of words, right? And so, so the way it does that is it uses a model. Oh, and the way it does that is it looks at words, it learns from text. So it looks at words, it looks at how they're used in the wild, and it looks at the context that they're used in, and then it tries to learn that context by trying to predict it, right? So this is a model to, given a word, predict the context. And that's the skipgram formulation of Word2Vec in particular. So if you think of a piece of text, you take the input idea, the model takes an input word and then tries to predict the context words that surround that word. So let's look a little bit in more detail at what this model is doing. So the input is one word, just one word, right? And that word is represented as a v-dimensional one-hot encoded vector. So v is the number of words in the vocabulary that we've chosen to use. You have a v-dimensional vector. Every entry in that vector is 0, except for the one spot that corresponds to the word that this vector represents, and that spot's 1. Right? So you have this v-dimensional vector. Now you have a matrix W that projects that vector into an n-dimensional space. N is a much smaller dimension. And then you have another matrix that projects out, a matrix of weights that projects out onto this output vector, where then you get a score that, again, you have a v-dimensional vector, so there's a spot for every word in your vocabulary. But now you have a score for each word, and you can use softmax to get a probability for each word. And so you have that for each of the context outputs. So what does it mean to train this model? Training this model means you take a word, you try and predict its output context words, and then you learn the weights on those matrices in order to minimize the output error in predicting that context word. And then you do that on a series of words, like over a whole, corpus of text. So let's look at the funny thing about that is, like, nominally, if you look at this model, it's a model for predicting the output context words, but like, who uses it for that, right? No one uses it for that. That was almost just like, the fact that we went through that exercise was just to like let it practice predicting context words, not because we care what it predicts, but because we wanted to give it a chance of learning what the context is for any individual word. So all the magic is really happening at this first W matrix that's projecting. If if you look at what it's doing, it's taking this vector in this sparse, one-hot encoded vector that's like really a categorical representation of a word, and projecting it into this space that's a continuous distributed vector space representing the word. So that looks familiar, right? That's exactly what I'm looking for. So is there any hope of this working in my problem? So language makes sense, right? The way that this works is the model is learning the context for words because the way that the word is used generally makes sense, so the context generally makes sense. It's pretty rare to have some set of words where, to have some written text where the words are just total gibberish. And you wouldn't really want to train your model on something like that. But do web histories make any sense? I mean, there's a lot of, if you look through, this is kind of excerpted from real cookies in our data set, and there's a lot of gibberish in there, right? Someone goes to babydames.net and then they go to miningglobal.com. Like, does it make sense to try and extract any meaning from context when the context looks like this? So there's one way to find out, right? Let's give it a try. So here's the history of one of the cookies. We start to churn this model through it. We input individual websites and try and predict the websites that are the context for that website. And we keep running it through a whole set of words, and we do this 15 billion times until we've trained some model weights and that hopefully have learned something meaningful about these websites. So this is what we get. And it's worth mentioning that there's a couple different sets of dimensionality reduction here, right? So in this case, we started with a 50,000 website vocabulary. That was like the dictionary you started with to predict. We trained the embedding into 128 dimensional embedding space. And then in order to get it up on the screen here, we did an additional step of t-SNE to get it into 2 dimensions. So that's a completely separate step of dimensionality reduction that lets us put it into 2D and make a little more sense of it. So we get this. Did it work? How do we know if it makes any sense? So one way to help us sort of, so the best evaluation method we really have is just our human brains and eyeballs to go there and see which websites, if the websites near each other are actually related to each other. A helpful tool in doing that is yet another step in dimensionality reduction, which is to take this 2D view and then cluster it into more clusters in this 2D space. So then we can look at individual clusters and see if the websites that cluster together in this space are actually related to each other. And if they are, that would mean that the model found something useful. So I'm going to zoom into this one particular box here. And the punchline is it really works. It's so cool. So if you look, all these websites are in this sort of pink salmon colored cluster there. And they're not just websites about travel, they're websites about like a particular type of travel, right? So boardingarea.com, thepointsguy.com, flightdeal.com, frugaltraveldeal.com. These are people who are not just thinking about travel, but they're thinking about how to stretch their dollar while traveling. It's like very specific. And the names for these categories I'm going to show are all human generated. So that's where kind of the manual labor comes in. So we can look at the next cluster over. Still, we're thinking about travel, but now it's a very different, still very specific type of travel, all about cruises. So we have princess.com, carnival.com, celebritycruises.com. So very specific, very tightly clustered, right? Very similar websites. Here's another one. The next cluster over is now destination weddings. So we see destinationweddings.com, we see Tahiti.com, endlessvacationrentals.com, very specific behavior, and then just one more. I could do this all, I can speak from experience. It's really easy to get lost in this and just find out oh, look, wow, did you know that there's a whole set of people that are into there's the whole internet's on here, right? And it's in these little clusters. I've learned so much about people in this job. So this one is still all about traveling, but now it's a specific type of touring and exploring type traveling. So we have Frommers.com, roughguides.com, all kind of similar, very specific type of travel websites. Okay, so this works. So this is a map. We made a map of the internet. And that's what we call it internally, at least in my company. And when we refer to it a lot because now we use it a lot. We use it for so much stuff. It is truly a map because a map tells you where you are. A map provides context. A map tells you what else is nearby. A map sort of summarizes things into the useful pieces of information you need. And so now, okay, to get into the uses for it, first we have to kind of recognize that there's two different worlds that it can live in. One is this 2D clustered into 800 clusters world, and the other is that embedding space, 128 dimensional world. And just in this world alone, there's so many uses for it because now we have a taxonomy of the internet. So now like we see an individual website and we can know what it's about and know what category it's in without having to like type into the URL and go to the website. And it is truly a taxonomy. It's not just a category, it's truly a taxonomy because you just saw all those different types of travel clusters were all next to each other and they all roll up into a set of clusters called travel. The whole thing rolls up into itself and we can really organize the internet. There's so many things you can do when you can do that. It's really hard to find like a good taxonomy in the internet. So one thing, for instance, so like in our space, okay, to start with, we can just target those people. So like a key business for us is creating predictive audiences for advertisers to target. So now, like these are all, like each one of these is an audience, right? You can set up a definition, like if you've been to at least 2 of these websites, now you're in the audience and we can target you. And that's really cool because it sort of blankets like all the possible behaviors really cleanly. Well, it's cool for targeting. Even cooler than that, it's cool for explaining models or adding like as attributes to describe other sets of users. Because of this fact that it sort of covers all corners of the internet, even corners of the internet that maybe no one would have thought of, like, you know, backyard chicken farmers or whatever. There's a whole cluster of people that are into very specific behaviors. So, okay, so for instance, if I make a supervised model to predict, you know, customers of a certain brand, and I want to understand if the model worked, I want to understand like what actually predicts customers of that brand so that I can go tell the client. If I make it in that original sort of sparse binary space, which is, we do all that, I mean, it's a great space for training the model in. When you go and look at the model, you just get this list of websites. It's a little hard to digest, but now we can slap on these categories labels, and it's like much easier to understand. And now we can actually intentionally go through that process, not just to create a predictive model, but just to describe a set of people, right? We can build a supervised model, layer these categories on, and now we can understand a group of people. And we can also, it's because it's this set of compact behaviors that describes like all internet behaviors, we can also use this as user level enrichment and ship it out to other partners. Like for instance, if there's a market research company that's doing surveys and they have like, they're collecting that survey data, we can ship to them at the user level also this observed behavioral data that they can append onto that. So it's like, because it's such a compact view, it's like very easy to do that, and it's, you know, can be really useful to them. Okay, I have to make sure to not run out of time. So, okay, so then that's just the way, like a bunch of ways we can use it in that clustering space. To think about how we use it in that embedding space, I want to think about not these websites in that embedding space, but the goal was to find a representation for users, right? So first, let's think about how we can get users into a continuous vector representation using this. So, okay, this is 2D. First, let's picture this in 3D, right? So stare at this for a second, kind of relax your brain. Think I'm staring at a cloud of 3D points on a 3D axis. Okay, so you have 3D in your head. Okay, now pretend that you can imagine it in 128 dimensions. For some reason, that's way easier when you go 3 dimensions first. Pretend this is 128 dimensions. So every website now has a home in this 128 dimensional space. And so if I consider one user, and they have a set of websites in their history, that's a set of websites, you know, that set of websites lives in this space. I can just take an average of those locations in this space, and now I have a vector in this space, and that's that representation of my user, right? So this is the picture that we were looking for originally. So what can I do with this? Now I can use this space itself actually as a space for a set of features for supervised learning problems, rather than going back to that whole sparse binary space. If I want a really compact space and I want like a low memory model that only has 228 features, I can use this space instead. Also back to that user enrichment problem. Now, if I want to be able to pass data to a partner to do their own modeling, I have this super compact information dense way of doing it where it's just 128 numbers per user. That's very easy to ship over. And then back to the original reason why we got here in the first place, right? We wanted to be able to find a way that we could define a meaningful distance between any 2 arbitrary users. And so this, we've got these guys into this space, we have that distance. Okay, so now I'm going to show you we're going back to that clustering world, that world of customer segmentation. I want to show you that when you have this vector representation of the users, that this thing actually works. So here is a project that we did for Oatly. Has anyone heard of Oatly? Yes. Yes. Okay. It's great, right? I love it. They're so great. So they launched in the US in 2017. They were a Swedish oat milk company, and they had a really cool way of launching. First, they launched in all like hip coffee shops in urban areas, and they got there first, and then from there they sort of spread out and spread their influence other places. So there was a moment in 2017 where they had kind of a steady set of a very interested set of early adopters through their coffee shop, like early launches. And they were getting ready for their real main launch, and they wanted to understand who their customers actually were as they planned for that launch. So it's a perfect opportunity for customer segmentation. So that's what we did. We did exactly the method I showed to you. We came up with this very cool dendrogram. And the one cool thing that came out right off the bat of this is, so you see I have like 7 clusters here, and some of them I have X's on, because some of these clusters actually weren't consumers at all. This came from people who went to Oatly's webpage like when they were new. So this is people who went to the trouble to go to the webpage, and so they're like truly early adopters. And so one of the clusters, and we wanted to understand what the US market looked like. So this tiny cluster is people who weren't from the US, and we could see that in their behavior, so we excluded them. And then the other 2 with X's on them are both, one was like food industry people who were, you could tell they read a lot of like food industry magazines, and they were interested in this new food product that was coming out. And then the other one was like us. It was like marketers and like advertisers and people that they were either directly working with for their launch, or who were like reading about the cool new way that they were launching in coffee shops and then going to their website. And I think it's really cool that they actually, if you look at where those 2, that cyan and magenta cluster, they're like actually right next to each other. So the non-consumer clusters, you can see that they're more similar to each other than all the rest of the clusters. I think that's really cool. But for Oatly, that's not what they cared about, even though it's what I cared about. What they cared about was, who are the actual consumers and what are they like? The problem is you have to understand who they are, right? So we've done this. Now we have these users represented in 128 dimensional embedding space. And like, so the one thing that we know about them is maybe like the average position in 128D space. It's not that useful to Oatly. So what we did is we took each of these sets of users, and we trained a supervised model to predict each one of these clusters. And we used a really simple explanatory model where we can then go back in and see what was predictive of being in that cluster and use that to explain what made someone in that cluster different from everybody else. So I'm going to show how we did it for this first big red cluster here, cluster 2. So we made a model to predict this. The model we made in that website space, that sparse website space, but we're able to then also make sense of it by layering on categories. So you see that here. And these people are into vegan stuff. Maybe not that surprising for a product that's like a non-dairy milk product, but it sort of makes sense, right? The thing that was surprising was that first group was into vegan stuff and food, but the other 3 clusters actually were not interested in food at all. Like the thing that was bringing them to Oatly had nothing to do with food. So that was a really interesting insight, and we were able to go to them and like tell them about all of the different types of people that were drawn to Oatly for different reasons, having to do with it being hip and new and cool, that had nothing to do with food. And by the way, all these descriptions you see here have nothing to do with machine learning. Again, we take our output and we hand it to people that are much better at writing descriptions and finding stock photos, and they make this lovely thing for the client, and the client likes it much better than if we just show them a list of websites. So we found this one set of people that are into vegan stuff, that like Oatly. We didn't really want to go back to Oatly and say, hey, we found that you have a lot of your customers are vegans. Where's my check? So I wanted to dig in a little bit more into these vegans and understand like what we could learn about them. So luckily, because of the way we did this clustering, we have this cool dendrogram. We can go back to the dendrogram, take that cluster and cut it a little bit lower, and get these 3 now like micro populations that all roll up into this, this sort of larger vegan population. And so if we look into what we got there, the first one is is people who are very interested in nutrition and very interested in the ingredients that are in their food. You see, so here I'm explaining it just by taking just screenshots from these web pages. So it's sort of another way to just kind of get a quick high level view of what's going on in those web pages without like clicking on every single URL. And these are what's going on in these web pages. You see people who are going to like professional nutritionist type sites, people who are really interested in like what actually is in the food nutritionally and like ingredients wise. There are some pictures of food on these sites. None of it looks very delicious. The second group is just so purely vegans that are trying to figure out how to be vegans. It's like all just vegan recipe blogs, and every single one of the blogs is like specifically a vegan recipe blog. And it's people who are like, I am vegan or I want to be vegan. What do I eat? How do I eat it? And they're on the internet trying to figure that out. There's food here and it's starting to look a little bit better, right? But then the third one is where the food really gets to look good. And these people actually, interestingly, are not vegans at all. So a lot of these people, even up here what you're saying is like cheese, it's like real dairy cheese. These people aren't drawn to Oatly because it's vegan or because it's not non-dairy. They're drawn to Oatly because they have an interest in like wholesome, organic, green food and community and cooking. And they have this very deep relationship with food that doesn't have anything specifically to do with non-dairiness, but it also brings them to Oatly and it draws them to Oatly. So you see there's these three separate groups of people, these three separate types of people that are all nominally, they're all sort of, to start with, nominally, everyone is like the Oatly early adopters. You dig in, you see one group of people is vegans, which is sort of to be expected. But then even among those, there's these three different types of people that are interested in this food. And they have totally different reasons for coming to that food. So as a marketer, you would want to talk to them in a totally different way, and maybe reach them in a totally different way. And so we're able to do this to find these different gradations in who's buying these products, because going back to this representation of like figuring out who's kind of different and kind of the same, even if they haven't been to any of the exact same websites, we can still measure the distances between any two set of people because of the way we figured out how to represent users in this high dimensional space. So I want to give one final example, a use for this. So now we're going from, before we had T-SNE'd into 2 dimensions and then did that clustering those 800 clusters in 2 dimensions. Now, and hopefully that this video plays because it's a cool video. So we made a augmented reality app, and it uses clustering in 3 dimensions, and it uses them as descriptive features to describe a set of users. So let's see if we can play it. So every sphere you see here is a cluster in that space. Oh, it came so close. Oh, see, I planned for this by having the actual video on my computer, but we couldn't make my computer work. Yeah, okay. Okay. Every cluster, every sphere is a cluster of websites, and then they're colored by how high they rate for that Oatly audience. So ones that are really blue are places on the internet where those Oatly users are more likely to be hanging out, and red is places where they're less likely to be hanging out. So then we can zoom in and like walk into the internet and pick one of these and see where the websites fall and what that cluster is about. So we have like gluten-free, vegan, recipe, healthy food, and then vegan, animal rights, right near those other like recipe and gluten-free sites, which kind of makes sense. Then we can go to a totally different region of the internet, and here's some that index high, and we have New York City, real estate, New York, furniture, which makes sense because of their early launch, right, in urban areas. And then we can go to a red area where they're not hanging out as much, and you see free cat videos. So like every part of the internet is represented on here. So we found a way finally to find the free cat videos on the internet where I can understand human behavior and how sequentially, I think what's really cool about this is the fact that the context that websites are visited actually do have meaning, and we can understand from that sequential visitation of how humans go through websites and what they go to, we can extract more meaning and context from the websites, and then use it to then organize the internet in a way like this that has tons of uses. So thank you. And I think it's just having a long time loading. Oh, it wants to play again. All I want to show here is this slide that says, if you want to talk more, I'm going to be at the O'Reilly booth at, what time? 2:40 today. I will be at the O'Reilly booth. If you want to talk more, you can find me there then. And also, by the way, we're hiring. So thank you.